Yeah, thank you, Mr. Chairman, for the introduction. So I'm Christian Liebold from Technical University of Berlin, and my talk is about atomic force microscopy and modeling techniques for the size effect in beam bending. So my outline is first a short motivation of the size effect in elasticity, I have to pronounce, and then to present some modeling techniques, as there are the strain gradient approach, for example, or micropolar approach, and also the coupled stress approach and surface elasticity, before I come to an experimental point of view, how to get some material parameter for real materials. Okay, as a motivation, I think we've seen such plots in further talks. So basically, as the thickness of some bending structures decrease, the bending rigidity can dramatically increase. And this is for several materials in literature, maybe for copper. I found something for epoxy. It goes on with silver and aluminum and, carbon nanotubes, as you want to model them by continuum mechanical approaches. And I started to build a list of material length scale parameters for certain materials, paying attention to slightly different theories behind these material length scale parameters, and of course to check the experimental design.
What is plotted on the axis? Charging.
You mean, and at what plot you mean? This is a diameter. So the diameter of a carbon nanotube, if the diameter decreases, Young's modulus. So in this test they checked, in this case they checked the elastic modulus and see how it increases. And a general observation could be that when you think of small microstructures in comparison to large microstructures, that also the material length scale parameter will increase. So in this, even up to the macroscopic scale in this case. So even if you have some beams of this size and you drill some holes in it, as I was inspired by Marcus Ariel, that had also a presentation here a few days ago of something the same. And I used these dimensions in some millimeters, so 2 millimeters as a whole diameter. And I checked the bending behavior of these rods by performing vibration experiments. So there is a free boundary condition, and when there's some impulse on this free boundary condition, it starts to vibrate, and by a microphone I get a fast Fourier transformation. You get the eigenfrequencies of the system. Here are 4 eigenfrequencies, and a very precise calibrated frequency measurement machine that gives you the first eigenfrequency. And out of Euler-Bernoulli beam theory, you can in the end calculate Young's modulus. Therefore you need to know the density of the material, the length is very important, and the first eigenfrequency you measure, and the thickness of the beam. And then, when I did this, I immediately get the bending rigidity that increase if the sample size decreases. And if I use the coupled stress approach, that is commonly the most easiest one at this stage, I will explain a little bit later on, gives you a fitted material length scale parameter of 1.5 millimeters. So something in the range of the microscale. Okay, then I want to speak a little bit about strain gradient approach in general. So, and I start with the generalized material equation for non-simple bodies of gradient type, as Ehringen pronounced it, and for the case here without memory effects and without temperature dependency. Then the stress tensor is a functional of the deformation gradient and the gradient of the deformation gradient. This is due to the non-simplicity of the material. And to build up the double stress tensor, this is a functional also on the deformation gradient and its gradient. Now, it's a clever idea to use reduced forms for this material equations. And for the small strain assumption, we can use the small strain tensor. And for the higher order terms, maybe Mindlin's second form of strain gradient theory that depends on the gradient of the strain. And then we can build, for example, a linear strain energy density for isotropic materials that is a function of, as I said, the small strain tensor and the first gradient of it. And by linearity, we multiply the stress and strain measures, and we see that we have two material parameters for the isotropic case in the strain regime due to the symmetry of the strain tensor. But we have 5 additional parameters for the strain gradients in it. And from this point on, for an experimentalist, it gets very hard to follow this idea. But altogether, I will fix that higher gradient theories depend on the deformation gradient and its gradient to build up a line element from the reference to the actual configuration. And here are no directors are used. As in the later on, we will see that we have to use directors. But to go one slide deeper in the strain gradient approach, I choose the strain energy density for the modified strain gradient model, as it was also given a few talks ago, as it was called simplified strain gradient model. And here we see that we have also a hook term, or not a hook term, this is the strain stress relation from conventional continuum theory, and we have gradients of the strain tensor. So, and by choosing this energy density, we can use Euler-Bernoulli beam bending assumptions and derive formula for beam bending. And out of this, we can calculate bending rigidities. And if we take such a bending rigidity here of the modified strain gradient model and compare it to the bending rigidity of the Euler-Bernoulli beam model, one gets such a formula that is mainly dependent on the thickness of the specimen, and here in this model also on the material length scale parameters. To get some feeling for these parameters, I choose to build the ratio of the deflection. This is the deflection of the present theory in comparison to the deflection of the Euler-Bernoulli theory, and I vary the length scale parameters to see which one is most dependent on it, and as people do it in literature somehow often, to equalize them. Okay, now I want to give a brief introduction to the micropolar approach, where the directors are used. So I will start on from the micromorphic continuum, maybe as the most general one for simple materials. And therein we need a deformation gradient to deform a line element from reference to actual configuration, and we need some tensor to build up the different directors, how they are changed. They can change angle and they can rotate, and this will build up the micromorphic continuum. If the directors are only used with stretch, we are at the micro-stretch continuum, and even if we fix the directors in their length and their angles with respect to each other, then we are at the micropolar continuum where we have rigid directors, and due to this also a rigid particle that it's just supposed to be able to rotate. And of course in classical Cauchy-Boltzmann continuum there are even no directors and no higher gradients. In the micropolar approach, I will start with the generalized material equation for simple bodies this time, also without memory and without temperature dependency, and we see that we have to take the first gradient of the first variables. Here it's the gradient of the motion, in fact, the deformation gradient, and also of this tensor Q that will describe the rotation. We need the first gradient of it. For the coupled stress tensor, it's quite the same, and I have to pronounce that the stress tensor now is a non-symmetric. And also here we can find suitable reduced forms due to some framework indifference considerations, and we will find a relative stretch tensor and a relative dryness tensor that depends on Q and the gradient of Q. So for the rotation of the rigid particle. Also here we can give a linear strain energy density for an isotropic micropolar elastic material, and here we have also to give all invariances of the strain measures material parameter, and we can identify maybe 6 unknown parameters in this theory. So also a problem for doing experiments on it. Now I want to go on with the coupled stress approach and simplify it immediately to the indeterminate model of the Kossera theory by putting the rotation vector to the macroscopic rotation vector. So this gives a dependency just on the displacement and the displacement gradients that will follow on. So there are suitable reduced forms for the small strain assumption. We can use for the stresses that are now symmetric again. We can show it by energy considerations. It's a function of the small strain tensor, and the coupled stress tensor is a function of the rotation gradient. The rotation gradient is built as follows. If we build the symmetric part of the rotation gradient, and we can enter the macroscopic rotation vector, and we see immediately that we have to deal with second order derivatives of the displacement field. What generally leads us back to the idea of strain gradients. And if we build in this approach the linear strain energy density for an isotropic coupled stress elastic material, we see lambda and mu as Lamé constants, and we have only one additional parameter for the rotation gradient. And this is a good thing to do experiments, and by taking Euler-Bernoulli beam assumptions we can also derive the formulas for it and build the bending rigidity of the coupled stress theory in comparison to the Euler-Bernoulli theory, and we have the same structure as for the strain gradient approach, and only one material length scale parameter in a combination. So I also did an FE approach for this coupled stress theory, and I used the open source solver Phoenix to implement the variational form of stress multiplied with strain that depend on the first gradient of displacement, and coupled stresses multiplied with the rotation gradient that depends on the second gradient of the displacement field. And with this, I had to use, of course, in the first war, C1 continuous elements. Okay, and I took a material length scale parameter that's quite big, so to say, 25 micrometers, but it doesn't matter for this point. And I get good beam bending displacement fields out of it, but I realized, as I checked for the convergence of it, immediately a dependency on the net, on the mesh, of course, and I checked that the element size somehow behaves like the size of the widget particle. We talked a few slides before. So remember the internal length scale I set to 25 microns, and here I have the thickness of the simulated beams, and here on this axis the percentile aberration from the coupled stress approach. And at the 0 point we have perfect coincidence, and this happens always if the element size is double the material length scale parameter. Here at constant ratios we have for one thickness, one element in the thickness direction, we have this curve, and for 2 and for 3 elements in the thickness direction. And if we now do the convergence, it's quite hard to understand, but if we increase the degrees of freedom stepwise, we start from such a good point, let's say, where the element size is identical to the material length scale parameter, we start at very good values for the coupled stress approach. That will be this line for bending. The Euler-Bernoulli approach will represent this line. And if we perform a conventional FE strategy with C1 continuous elements, we have immediately very good convergence on the Euler-Bernoulli beam theory. And if we increase the material length scale parameter, we have immediately very good values for the deflection of the beams. So there's another tricky FE approach when you want to use C0 continuous elements. You have to use a penalty constraint like parameter called P. Now the variational formulation is that the strains depend on the first gradient of displacement, and the rotation gradient still is dependent on a first gradient of the rotation. So this is why you can use C0 continuous elements, and in a penalty constraint term that you add in this energy, you will force somehow the rotation to be like the macro rotation vector. And this is, of course, a constraint of two former independent fields, phi and u. But now you have the choice for P to build up this error. And if you do so, again, we have the Euler-Bernoulli beam results, and you have the coupled stress results. The conventional FE strategy now have somehow a bad convergence due to C0 elements and tetrahedral element shape. But if you increase or set P to certain values, you can see how the convergence is dependent on this value, and you can find a good P value to have a good convergence to the coupled stress model and to do further things with it. So one slide for the surface elasticity. That is also a model to build up the size effect in beam bending. And there we use the surface stress tensor here with surface elastic moduli. Now everything's in 2D because we deal with a surface. So the equilibrium equations will be derived as follows, and the curvature tensor will be presented in this way, so that we follow the normal vector on the surface and its derivative in both directions, and if they do not change, we have a flat surface, we have no curvature. And by doing so, I found in literature also a derivation for the bending rigidity when you propose the surface elasticity just as an enhancement of the conventional continuum theory. So here are no higher gradients, nothing else but conventional continuum plus surface elasticity. And there we can also derive formulas for beam bending and beam rigidities. And I compared them to Euler-Bernoulli, and I get nearly the same dependency on the thickness, but it's now not square dependency. And the somehow material length scale parameter one can identify here depends on the surface elastic moduli and on the Young's modulus of the bulk material. And interestingly, the surface elastic moduli can also be set to negative values. And negative values somehow will mean a softer elastic response in the small scale that is also observed in some experiments. So, okay, and by saying experiments, I will come to my own experimental apparatus that I use. It's an atomic force microscope. It's a conventional atomic force microscope with a laser reflective system. Some call it beam bounce technology. You have a laser that shines on a very small tip, is reflected there, and the light is collected in a photosensitive detection system that consists of few diodes. Okay, here is a picture of it. You see how the laser shines on the specimen, and this is how the experiment works. Here I have a microbeam, and the AFM probe will touch this microbeam and bend it. Here's also a picture. This is all inside 1 millimeter here, for example. So it works as follows. In the PSD we collect the millivolt, sorry. It's an electrical signal of the photosensitive diodes, and if the laser stripe that shines on the diodes is in the middle of all diodes that are connected as a Wheatstone bridge to measure the electrical signal there, then we have quite linear behavior of the signal. But altogether we have a non-linear response, so we can start here our measurement and bend the AFM probe to here, or we can start here and bend it here. It depends on every experiment. What we get is an information about how we lift up the specimen and how the AFM probe is bent, so an electrical signal U. By calibration of this signal, we can get forces out of it. And if we test now a rigid surface, this will be the blue line here, and then after this we test the structure, the microstructure, it is not very hard to see that the difference at every point here will be due to the bending of the microstructure. And this is exactly the information we need to build an experimental derived bending rigidity. So, and we can compare it to the chosen coupled stress bending rigidity, where there's only one material length scale parameter. And by doing so, for the materials, I tested silicon in a range of maybe 1 to 8 micrometer, and for silicon nitride in the range of 200 to 800 nanometers in beam thickness. I detected no size effects in this range. And yeah, altogether, what I want to do in future is to have experiments here for epoxy, and I can model them with analytics and with an FE strategy. And this will be my task for the future, to do it on epoxy as well. And as SU8 is another polymer, I get a nanoporous nickel alloy, and I want to do it on aluminum foam. And of course I will follow the idea on the C0 or C1 FE strategies also for the full strain gradient or the modified strain gradient model. So with this I say thank you for your attention.
This is very interesting. I don't understand when you're saying element size is like a rigid particle. I don't understand this question. Can you explain?
Yeah, I mean, when you have an element size and you want to model very thin structures or very small structures, then you have to be aware that one element somehow represents the micro widget particle. So the finite element, the size of the finite element.
Finite elements are deformable.
Yes, but this maybe is due to the combination of the pseudo-Kossera approach. So it's not you cannot distinguish anymore between rotation and displacement due to the fact that I used the macro rotation vector to replace the micro rotation.
Okay, so
this is.
So you have a beam which discretizes into finite elements.
Yes.
There's three beams you show.
Right.
Finer and very fine.
Yeah.
And so what do you mean by? So finite elements are deformable and the rigid particles are not deformable.
Yes, I mean.
So what do you mean by is it equality there in the middle of the gray box or roughly?
Yeah, so I mean when I have the material length scale parameter of 25 microns, and I want to model a beam that is 75 microns, then I have to use 3 elements.
Okay.
3 elements in thickness to get the same values as the coupled stress model will give me. So, and when I use a beam thickness of 25 microns, I can only use 1 element in thickness, because otherwise it will converge to the Euler-Bernoulli beam assumption.
Okay. I think I understand. Other questions?
Just a remark on the coupled stress model. I think that is a very difficult choice to take such a model because it has a singular stiffening behavior when you have very small sample sizes. So you cannot apply the model for actual sizes which are smaller than RBE. It will have, you saw it in the beginning, it will have a singularity.
Yes.
Again.
I think here. Right.
And the question which I would have is what's really happening, or what would you like to have if you go to 0? Should it go into the singularity, or should it switch back to a finite stiffening behavior?
Yeah, this is.
And there are models which have a finite stiffening behavior, and there are others which do not. And the coupled stress model is just the worst one with the worst singularity. In a micromorphic model, for example, you can have a finite stiffening. And that will, of course, influence your determination of parameters. Think when you do an experiment with very small sizes, you are running in the singularity and your parameter estimation will be very sensitive to where you have been. we don't want to have that, but yeah.
Another question?
So I was wondering to what extent you are measuring the constants as part of your theory, and the whole thing is somehow kind of fitting of itself. Can you use any of these to predict something completely different?
Yes.
Like what?
Yes. Like I did this FE approach, for example, also for plate modeling. A Kirchhoff plate model, for example. If I once have the parameter, the material length scale parameter, I can do other geometries, for example.
And you get good agreement with that?
Yes. Yeah, but I have no experiments on microplates. Is a hard thing, so I cannot correlate to experiments very much.
But then if you don't correlate, then you are not answering.
No, just because of other problems from an experimental point of view.